Good day everyone. Welcome to Engineering e-learning channel. I'm your instructor, Sergio Maghanoy. For today's lecture, we're going to discuss about electrical resistance. Electrical resistance related to board exam problem. Okay? So we all know that board exam is a number game. The greater the number of problem you solve, the greater of chances in passing the board exam. But it is not only how many problems you solve, but how many theories you understand, the process itself. Okay, so let's start with our discussion with the formula of our electrical resistance. So to recall, our electrical resistance formula is equal to, resistance is equal to the resistivity times length all over the cross-sectional area. The second formula for our resistance is resistivity times volume all over the square of your cross-sectional area. And the third formula is equal to resistivity times the square of your length all over the volume. Okay. So one of technique in memorizing formula is not just memorize the formula itself, but in order for you to recall the formula correctly, you should know what are the parameters inside each component of the formula. Okay, that is our topic for today. We discuss the parameters, the attribute inside each component of the formula. Okay, so let's start with the resistance. What is the unit for our resistance? Ohms, yes. So our R, the unit for our resistance is in ohms. What are the other factors related to our resistance? Or what are the factors that affect the resistance of our conductor, for example? Okay, if we take a look at our formula, one of the components that affect your resistance directly is your resistivity. It is present in your numerator side. It means it is directly proportional. Your resistance is directly proportional to your resistivity. What is this resistivity? Resistivity is the properties of your materials. Okay? For example, our copper. Each material, copper, aluminum, silver, have their own different value of the resistivity. So, means our resistance is directly affected by our resistivity. What other factor that affects our resistance? Yes, the cross-sectional area of your conductor, or whatever the shape of the material, whether it's a cylindrical shape, it's in bus bar shape, or in a cubical shape. Okay, so it is inversely affected by the cross-sectional area. Other thing also is the length of your conductor, or the length of the bus bar, or the length of the aluminum sheet or the copper sheet. So length is directly, your resistance is affected by the length directly. So these are the things that affect the value of our resistance. What other factors that affect our resistance? Aside from the resistivity, the properties of the material, the length of your material, the amount or the volume of your materials. What other factors? Yes, the temperature. The temperature affect the value of our resistance. Okay. Okay. What is our next going to discuss? By the way, the reciprocal of your resistance, um, the reciprocal of your resistance is your conductance. Okay? So it means that your the reciprocal of your resistance is your conductance. What is the unit of our conductance? Yes, the unit for our conductance is inverted ohms. But nowadays, the unit for your conductance is in Siemens. Okay? Siemens. So, what is the formula for your conductance? Your conductance is equal to the conductivity cross-sectional area all over the line. It is almost the same with your first formula. It is in reciprocal form, inverted form. Even the units before, it is in mho instead of ohms. Right? And don't forget about your conductivity. Your conductivity is equal also to the reciprocal of your resistivity. Okay? Your conductivity is equal to the reciprocal of your conductivity. Okay? So again, our conductance, the unit of our conductance in old version, mho, and in the new version, Siemens. Okay? So conductance is equal to your conductivity times the cross-sectional area all over the length. Or your conductivity is the reciprocal of your resistivity. Okay? So, I think we can move on to the other component. Okay. Let's deal with our resistivity. Okay. Resistivity. So, resistivity, it means each material have different resistivity. For example, for copper, our resistivity for copper is 1.724 micro ohm centimeter. Okay? So, let's not forget our value of our resistivity because there are problems in the board exam that will not give you the value of your resistivity. So, it is your task to memorize the value of your resistivity. But this is very common. We only have two common materials. We have our what? Aluminium. Okay? Aluminum. Okay. So, other form of our copper resistivity that we need to memorize is 10.37 ohm is in circular mil per foot. So this is the two value of your resistivity that you need to memorize. Of course, once there is a unit involved, conversion factor follows. Okay? So it means that the reference, for example, if the resistivity given is 1.724 micro centimeter and your length and the details of your cross-sectional area is in different units, you need to convert a line to your resistivity, which is your centimeter unit, or the other way around, in circular mil or in feet. Okay, so your reference will be your resistivity, or if you want, you can do it in the reverse side. You can do your reference in length or in cross-sectional area, as long as you properly eliminate the units using your common conversion factor. Okay, so resistivity. What are the things that we need to deal with our resistivity? The common unit for resistivity is ohm centimeter. Other are in ohm meter. Okay. So resistivity. The next is your length. For your length can be an indicator of what type of material you are dealing with. For example, if you have too much length, example, 300, 400, 500 feet length. So, that length is too much for a specific bus bar. So you can assume that with that length, the problem is specifying that it is a conductor. Right? Okay. So length can be an indicator of what type of material you are dealing with. If the length is too short, yes, it can be a bus bar or other electrical component made of copper or aluminum. Okay, so length can be an indicator. What is one of the important things in this formula is our cross-sectional area. How we deal with our cross-sectional area. Okay, so let's deal with our cross-sectional area. So our cross-sectional area. So start with the cylindrical shape, which deal with the cross-sectional area and the volume because they are uh, related, the volume and the area. Okay, so let's start with the cylindrical shape because common shape of a conductor is in cylindrical unless it is specified with a specific shape. Okay, but conductor, you can safely assume that it's in a cylindrical shape. Solid conductor is in cylindrical shape. Okay, so if this is a cylindrical shape conductor, we have a diameter here, right? And you have a length. And you have a radius here. Okay, start with the cylindrical conductor. We all know that the formula for our cross-sectional area for our cylindrical conductor is pi r squared. Now, if in the problem, the given is in diameter, you need to modify also your cross-sectional area formula, okay? So, what will happen? Your phi is equal to your diameter over 2 squared. Or if you apply the power, that would be phi d squared over 4. Or simply, if you rewrite your cross-sectional area, that is 1/4 pi d squared. So, your cross-sectional area, you're talking about, you are identifying this portion, that is the cross-sectional area. Now, the unit for your cross-sectional area should be in, the power of cross-sectional area should be in square, and the power of your volume should be in cube, right? Means that in order for you to determine the volume of this cylinder, you need to multiply it with your length. Yes. So therefore, your volume for your cylindrical conductor would be your 1/4 pi d squared times your length. The unit will be in cube. Yes, you have your volume which is related to your formula. Okay? Because the problem will always, they'll give you a twisted problem. It's either one of the parameters is unknown, the two other parameters is given. So you need to know how to manipulate this parameter in order for you to arrive to determine your unknown if it is resistance. Okay? So let's move on to other shape. If you are given with a cube, we all know that cube is all equal with each side. So your depth, your length, and your width. Okay? Okay, so your cross-sectional area here of a cube is equal to your width times your depth. Okay, so the unit here should be in squared. Now, if you want to determine the volume, your volume would be, yes, in solid mensuration, you already did this. So that would be width, depth, and your length. Okay? So that would be your volume. How about the common shape? A bus bar. Okay? So if we have a bus bar, so we have our length, we have our width, and we have our thick, the thickness of your bus bar. So in order to determine the cross-sectional area of your bus bar, your cross-sectional area is equal to your width times the thickness. Okay? Or if the volume, if you're after for the volume, that is your volume is equal to width, thickness, and your length. Okay? So cross-sectional area. How about if you're dealing with the volume? If you're dealing with volume, you need to recall the formula, your weight density is equal to your total weight over the volume. Okay? So don't forget about this formula. Kindly refer to my sample problem solving and using this formula. You have the total weight, you have the volume, and you have the weight density. Okay? The weight density. This is the formula related to your volume. Okay. What if you're given a problem related to your resistivity? For example, if your resistivity is made constant, let's start with this formula. If our resistivity made constant, resistivity length all over the cross-sectional area. If your resistivity will become K or your constant, what will happen to your formula? That would be R K L over the cross-sectional area. And if you transpose your formula with respect to your constant, what will happen to your constant? Therefore, your K is equal to resistance times the cross-sectional area all over the length. This can be your starting point if you're solving a different conductor with the same resistivity. You can use this condition. For example, if you have two different conductors, you can use this you can transpose that condition to, for example, if you have two different conductors, you can use it R1 cross-sectional 1 all over the length of your first conductor, and your R2 A2 all over the length of your second conductor. Here, make sure that you deal with the cross-sectional area properly. You need to identify your cross-sectional area accordingly, if it is a cylindrical, a cube, or a bus bar shape. Okay? So, deal with your cross-sectional properly. And make sure that if you're using this formula, so K is the resistivity, make sure if you're using this formula, you need to eliminate the units properly. Both sides should have an equal or the same units for you to eliminate both sides properly. Okay, what are the things that we need to remember about the other two formula? These two formula is used in your conductor under drawing process. Drawing means if a conductor is being drawn to a smaller diameter. It's one of the process in resizing the conductor in the production area of your conductor. So drawing process is being stretched. So we use this formula, but here with these two formula, the constant is the volume, the resistivity and the volume is made constant. Okay? If you recall the formula for drawing a conductor and you are tasked to determine the resistance of the first conductor or the second conductor. So the resistivity and the volume is made constant. So if you remember the formula, R2 over R1 is equal to your length 2 over length 1. This is in second power. This is one of the formula of drawing process of a certain conductor. The second formula is your R2 over R1 is equal to your diameter 1 over diameter 2 to the fourth power. So these are the formula used if you are dealing with a conductor under drawing process. But wait, this two formula is derived from these two formula. Okay? So let's not forget, you can derive these two formula from these two formula. Okay? So let's try to solve. If our volume and resistivity is made constant, our R is equal to resistivity times volume over the square of your cross-sectional area. Then your resistivity and volume is made constant. So what will happen? So your R become your K over your square of your cross-sectional area. And if you transpose the formula with respect to your constant, therefore your K is equal to your R squared of your cross-sectional area. Now you can use this in solving two different resistance or different conductor given. So you can use it like, if you transpose this formula, you can have your R1 A1 squared is equal to R2 A2 squared. But wait, conductor under drawing process, it means that conductor, it is in cylindrical shape. If we recall our formula for our cross-sectional area, this one, if you recall the value of your cross-sectional area, if you're going to use that, your cross-sectional area is equal to 1/4 pi square of the diameter. So you're going to substitute your value of your cross-sectional area to your condition. So what will happen? Your R1 will become 1/4 pi d squared R2 1/4 pi d squared. Okay, so what will happen? We have a common value. We cancel out 1/4 pi, we cancel out 1/4 pi, and we apply the power. So your value now, your condition is equal to your d1 to the fourth power and R2 to the second diameter to the fourth power. If you're going to rearrange this condition, that would be your second formula in drawing process. Okay, let's start with R1. We eliminate R1. R1, both sides, R1. So the remaining is D1 over D1 raised to the 4 is equal to R2, R1, D to the 4. Then we move to eliminate our R2. So we eliminate our R2. Eliminate our R2. Sorry, not R2. Okay, let's rewrite. Your D1 to the 4th is equal to your R2 over R1, your D. If you transfer your second diameter to the other side, so what will happen? If we cancel out, your formula would be R2 over R1 is equal to D1 over D2. Wait, you have the same power properties of your power. You can copy the power. So now, you already derive your second formula, which is this one. Right? Same process in dealing with in deriving this formula. If you want to derive this formula with your length, now with our formula R is equal to your resistivity, square of your length over the volume. You made your volume and the resistivity to K. So what will happen? Your R is equal to K square of your length. Therefore, your K is equal to your R all over the square of your length. Now you have this condition. Okay? So what will happen? You can use it if you have a two different conductor under drawing process. So you have your R1 over your length 1 squared is equal to your R2 over length 2 squared. So you what? Transpose. For example, if you cross multiply it, what will happen? That would be your R2 L1 squared is equal to your R1 L2 squared. So if you all over R1, and your, what will happen? Your L2, your L1 squared, and your L1 squared. So you cancel out your R1, you cancel out your L2. What will happen? Your R2 is equal to your R1. On the other side, your L2 over L1. With properties. Properties of a power. So you copy the power. Okay? So that is your first formula. Here. So that is the same. So it means that you only need to remember these three formula in order for you to have a different useful condition. If it is a constant resistivity only, you can deal with this formula. You can do also this process here. Okay? If you made your resistivity constant, you can do it like this. And this third formula, if your resistivity is constant, you can do this process. Or if in drawing process, both the resistivity and the volume, the resistivity of the volume, you can determine these two formula. Okay, so that is our electrical resistance in ohm. What are the other things that you need to remember? If you're dealing with your resistivity at micro-ohm centimeter, so what are the common conversion? Okay, so if you're dealing with your ohm centimeter, 1.724 micro ohm centimeter, or in meter, you need to know some basic conversion. For example, for your 1 inch, that is equal to 2.54 centimeters. So if the given is in inch, you can convert it back to centimeter, then you can cancel out centimeter. Okay? So what are they? 1 feet is equal to in inches. That is equal to 12 inches. What are the other conversion? For example, if you have a meter, 1 meter, that is how many feet? That is equal to 3.28 feet. How about if it is in miles? If you have a 1 mile, that is equivalent to how many feet? That is 50 to 80 feet. Okay? So, don't forget this common conversion. What if you're dealing with your ohm in circular mill? Okay? Common conversion. What if you're dealing with your ohm circular mill? If you're dealing with the circular mill per feet, For example, your resistivity of copper is equal to 10.37 ohm in circular mil per foot. If you're dealing with this, the unit is of our resistivity is in circular feet. Don't forget our conversion. In every inch, here is a 1,000 mils. Okay, in every inch, there's 1,000 mils. Okay, so in every square inch, how many circular mil? There are 1, 2, 7, 3, 2.4 circular mil. If you're dealing with your circular mil per foot, the foot can be dealt with, but the circular mil, you need to remember this. Okay? What are the other things that you need to remember in dealing with the resistance problem? Okay, also, um, if you're dealing with a cable, a cable is in cylindrical shape, right? So if you have a cable, you have your the so this is your radius 2, and the radius from the center of the cable going to the skin of the cable. So that is your R2. And your R1 is the radius of your conductor inside the cable. So this is your R1. And the formula for your R in a cable is what? Almost the same with your formula. That is equal to what? The resistivity all over 2 pi, because that is in two different radius. From the center of the cable going to the first radius of your conductor, and the second is from the center of the cable going to the skin of your cable, that is your R2, which is equal to resistance is equal to the resistivity all over 2 pi ln radius 2 over your radius 1. So that is the formula for your resistance if you are dealing with the cable. Okay, let's recall if you have forgotten anything. So cross-sectional area, you need to deal with the cross-sectional area. If you're looking for your volume, refer to your cross-sectional area, multiply with your length. If you're dealing with a conductor under drawing process, you can derive the formula. R2 over R1 is equal to your length over length 1 squared, or in diameter details, R2 over R1 is equal to D1 over D2 to the 4th power if your conductor is under drawing process. Okay, so we have the cross-sectional area, common conversion factor, the reciprocal of your resistance. If you're dealing with a circular mil, don't forget the conversion factor. If you're dealing with a cable related to resistance, resistivity over 2 pi ln over R2 over R1. So this is the formula if you're dealing with a cable. Again, okay, the formula for your resistance when it is affected by a temperature. Okay, so the formula for your resistance is affected by temperature, that is R2 over R1 is equal to 1 plus temperature coefficient times the change of your temperature. The change of your temperature. Okay, you can use it also, and don't forget about the constant of temperature coefficient. Your temperature coefficient is equal to 1 all over the inferred temperature at plus your reference temperature. Okay, so that is your temperature coefficient. Please refer to our example problem when using your formula when related to a temperature. So did you forget anything about our resistance affected by the cross-sectional area, resistivity of materials, length, volume or the temperature. Okay, drawing process, the cross-sectional area, I think it's clear. Common conversion factor, condition when your resistivity is constant with two materials. Okay, so I think I've discussed almost everything related to resistance. If I forget anything, just comment down below and we will discuss portion of it. So that would be all for today. Thank you everyone.